Hi, I'm Mengyu. Today I'll talk about improving the computational efficiency of an inspection planning algorithm that combines sampling and search-based approaches. This is a joint project with University of North Carolina and Israel Institute of Technology. In the case of inspection planning, we have a robot equipped with a sensor, and we are to inspect a set of points of interest in the environment. Inspection planning has many applications. For example, from using unmanned aerial vehicle with an onboard camera to the structural inspection of a bridge, all the way to using a medical robot with a chip-tip camera to do endoscopic tests inspecting human anatomy. Why is inspection planning hard? First, to inspect these complex structures, the robot has to move in a geometrically complicated environment. From an algorithm point of view, considering the points of interest to inspect, the size of search space for motion plans increases exponentially. And the optimality inspection planning considers not only inspection but also efficiency. The primary goal is to inspect as many points as we can while considering the sensor constraints. And as an additional goal, we also have to consider plan length, which could correspond to procedure time or distance traveled by the robot. For example, we need to consider battery constraints for mobile robots. It is even more important in the medical case, since the procedure should be completed as fast as safely possible to reduce costs and improve patient outcomes, especially if the patient is under anesthesia. In 2019, we proposed an inspection planning algorithm, ARIS, which stands for Incremental Random Inspection Roadmap Search. ARIS reasons about inspection average and plan length simultaneously, and it provides asymptotic optimality. The paper I'm presenting today is built upon ARIS, so let's first take a brief look at the original algorithm. In ARIS framework, we iteratively densify a roadmap and do graph inspection search, which computes inspection plan on the roadmap. How do we incrementally densify a roadmap? We basically build a rapidly exploring random tree, namely connecting new samples to the tree via its nearest neighbor. And this tree then implicitly defines a rapidly exploring random graph by adding edges from the newly added vertex to multiple nearest neighbors. For this roadmap, each vertex represents a configuration, which is a set of parameters that uniquely defines the state of the robot. Each configuration is also a viewpoint for inspection, since for a given configuration, we can compute the set of points of interest being inspected. Back to ARIS framework, doing graph inspection search for the optimal plan is computationally hard, so the key insight is to compute near optimal inspection plan instead. Two approximation parameters are used to bound plan length and inspection coverage respectively. More specifically, epsilon guarantees the search result is at most 1 plus epsilon times the length of the optimal plan, and P guarantees the search result has an inspection coverage whose size is at least P times the size of the optimal inspection coverage. With these parameters, we reduce the search space significantly. Furthermore, we do parameter update at every iteration to guarantee asymptotic optimality. The original ARIS was compared in simulation with the previous state-of-the-art method, rapidly exploring random tree of trees, in short RTOT. We first looked at, when given the same computing time, what is the inspection coverage. Here we use a logarithmic time axis. ARIS results in more than 10% coverage, better than RTOT. And to get the same coverage, ARIS is more than 25 times faster than RTOT. Also, ARIS produces plan with similar length as RTOT. However, when we look at the computation time decomposition, it is obvious that as the roadmap grows larger, the time spent on graph inspection search gradually becomes dominant. So the next question is, can we improve the computational efficiency of ARIS? To answer this question, here comes the paper I'm presenting. Recall this is ARIS framework, so the first thing we can do is optimizing the roadmap construction, building a more inspection-informative roadmap. Then we can also improve the search efficiency From the computation time decomposition, speeding up the search seems critical. To build a more inspection-informative roadmap, we use a simple yet effective method called coverage-informed sampling. In the original errors, any random sample is accepted, and we try to add it to the roadmap. With coverage-informed sampling, we check for a random sample if any previously uncovered point of interest is inspected from that configuration, and decide to accept or reject the sample accordingly. This check simply reduces the number of configurations needed to achieve a large overall inspection coverage. However, deciding if a sample is accepted purely on inspection contribution breaks the asymptotic optimality guarantee, so we always directly accept a random sample with some probability. To understand how search efficiency is improved, we have to take a closer look at the near optimal search in the original errors. On the roadmap, there are configurations. Each of them inspects a set of points of interest. There are also edges connecting the configurations, noting the transitions between them. Both inspection coverage and plan length are optimized during planning. When we do graph inspection search, each node in the search tree represents a trajectory on the roadmap. For example, the root node has only vertex A, and the trajectory represented by a search node grows longer and longer. For better inspection, we might need to revisit a vertex. In this example, we need to revisit A after visiting B to further explore C or D. Since loops are allowed, an incredibly large search tree might be built for such a simple roadmap. The original arrays used multiple techniques to prune away nodes. Strong domination prunes away nodes that are absolutely not promising comparing to other existing nodes in the search tree, but pruning away only strongly dominated nodes is far from sufficient in most cases. Here comes the near optimal relaxation using P and epsilon. Weak domination prunes away much more nodes, shown in yellow here. For more details about the pruning techniques, please refer to the original paper. We need to be super careful when we apply weak domination, since error accumulates as more dominations happen. In this example, each circle is only slightly smaller than the previous one, but finally circle D is much smaller than circle A. To solve this error accumulation, we have circle B keeps a record of A and so on. This nested bookkeeping enables circle D to access the information of A. In the original arrays, such bookkeeping is done in an operation called subsuming. After all these details, we can explain how the search algorithm is improved. The original arrays checks whether an edge is valid only when a result plan is found. When the result plan contains an edge that is not valid, the search is rerun from scratch. We refine this lazy edge evaluation by doing edge evaluation during the search in a lazy A star style. However, if we only do edge evaluation when expanding a node, for an invalid node, we need to extract all the bookkeeping it has and roll things back. So instead, we perform edge evaluation both when expanding a node and when a node is subsuming another node. This requires no additional bookkeeping and rolling back. Another technique we use to improve search efficiency is reusing search efforts across iterations. In the original arrays, new nodes are incrementally added to the roadmap, but every search iteration is run from scratch since the approximation parameters are also updated. Tighter approximation means some weak dominations in the previous search iteration no longer hold. So we developed a non-trivial search reuse method to fix subsuming that should not happen with the latest approximation parameters, and further takes into consideration the newly added samples. This is done with 4 steps. First, we put violating branches into a recycle list. Then we recursively fix violating nodes in the recycle list. After that, we reinsert fixed nodes to the search tree. Finally, we insert nodes that involve new vertices on the roadmap. The first 3 steps account for updated approximation parameters, while the final step accounts for updated roadmap. We did simulation experiments on 2 inspection tasks. The first one is bridge inspection with an unmanned aerial vehicle. The second one is pleural cavity inspection with the Continuum Reconfigurable Insertionless Surgical Parallel Robot, or the CRIS robot in short. Pleural effusion is a serious medical condition which causes the collapse of the lung. To accurately diagnose the cause, physician needs to visually inspect the inner surface of the pleural cavity, the space between the lung and the rib cage for a patient whose lung has collapsed. Inspection planning for the CRIS robot is hard, not only due to the nature of the inspection planning, but also because its kinematic computation is expensive. We compare the improved version of ARIS with the original ARIS and also RTOT, the previous state-of-the-art method. For bridge inspection, the updated ARIS is 570 times faster than the original ARIS, and it produces results with similar length for different inspection coverages. Finally, we look at the computation time that is spent only on search. The search efficiency is improved by 830 times. For pleural cavity inspection, the improved ARIS is 6 times faster than the original ARIS, and the plan lengths are similar. Finally, the search efficiency is improved by 3,200 times. All our code, including the original and improved ARIS, is available on GitHub. Thank you for your time, and I'm happy to take any questions.